So here we're going to take a look at atomic radii and specifically why atomic radii vary in size, even for a given atom of a given charge. We're going to use this very nice diagram from the online mineralogy textbook by Dexter Perkins, where he shows, let's take sodium as an example here, when it's in fourfold coordination, that's that first number in the first column, we have a radius of 1.07 angstroms here, but if it's in sixfold coordination, it's a tad larger, and if it's in ninefold coordination, if sodium is surrounded by 9 anions instead of 6 or 4, it has a much larger radius, 1.4 angstroms. So what's going on there? It's all sodium, same atom, same charge, all 1 plus. So what's going on? Well, let's draw a sodium atom here, and then let's say we have a number of anions that are surrounding it. We'll just put them out here. They don't necessarily have to be in close contact for the purposes of our illustration. If these are all negatively charged atoms, if these are all anions, they are wanting to pull away electrons from, let's say, a positively charged atom here. And as these negatively charged guys interact with the outer electron shells of the sodium atom, the more anions we bring in to surround this fellow, then the more tugs there are, they're going to pull that electron cloud out to greater and greater radii. So you have this tugging effect where the electrons that are surrounding that sodium atom are going to be pulled outward towards the surrounding anions. So the more anions we have surrounding a cation, then the bigger the effective radius will be. Now you might see that that actually presents a bit of a problem. In another video, we talk about so-called radius ratios, where we look at the radius of a cation shown as R sub A versus the radius of an anion shown as R sub X, and that's supposed to get us to a coordination number, and yet we need the coordination number to know what radius to use. So that's a bit of a circularity. Not a bit of one, it's a major circularity. So how do we get around that? Well, we don't. The problem is always going to be there. And the way we're going to use radius ratio rules is sometimes we just have to guess at the coordination, and then we'll look at various kinds of calculations and then see what makes sense. Now, that is just one effect. So atomic radii can be affected by coordination number, but then there's also the effect of charge. The greater the charge on an atom, so if you take a look at magnesium over here with a 2 plus charge, then the smaller the cation will be. If we have 2 plus charge here compared to the 1 plus charge, notice that all of these fellows, the sodium, are all greater than 1 angstrom. These fellows are all less than 1. The potassium atoms here are all about 1.5, and then all the calcium fellows are less than 1.5. And then if you move off to things like scandium or chromium with a +3 charge, you can have even smaller radii. So the more electrons we strip away, basically, the more strongly positive the charge. So the more strongly, we'll write it out, positive the charge, then the smaller the radius. Now there is one other final contribution to the atomic radius, and it's also affected by this total charge here. If the best example are the so-called rare earth elements, we'll just abbreviate as REE, which we talk about in another video. So those are shown, they're out of view, they're at the bottom of the chart where we're filling the f orbitals, where we go from lanthanum to lutetium. All of these fellows have a 3 plus charge, the charge is constant, but the radius of lanthanum is much greater than the radius of lutetium. And the reason why is because lutetium is a bigger atom. So let's say we have X number of protons sitting in the nucleus, and so we have some kind of electron orbital here, and then there's some other atom that has precisely the same charge, but it has fewer protons in the nucleus. And so there's the electron orbital there for our second atom. If we have more protons in the center of this atom here, it's going to pull those electron orbitals in, whereas if we have fewer positive charges over, in this case over here, let's say for the case of lanthanum, then there's going to be less strong of an electrostatic charge, electrostatic force between the nucleus and the electron orbital, and that'll cause the atom to be a little bit greater. If the electrons are not as strongly bound by the nucleus, then they can occupy a greater space. And that would be why the radius of lanthanum is greater than the radius of lutetium. We can write that a little bit better. Radius of lanthanum greater than the radius of lutetium. So you could take a look at the bottom of a periodic chart like this, and just keep in mind that with few exceptions, all those fellows are going to be of a 3+ charge. So there are three basic effects. There's the coordination number, there's the total charge. The stronger, the larger the coordination number, the bigger the atom, the more strongly positive the charge, then the smaller the atom. And then we have this effect of the nuclei pulling in on the electron orbitals. The more nuclei we have, in other words, the greater the atomic number, then the smaller the radius. So coordination number, total charge, and atomic number are all going to affect the atomic radius.